All right, so it's time to start our GCAS seminar. So today, we have a new speaker from Penn State University with Professor Dong-hee Chung. So here, talk about the searching for dark matter black holes called IGWN LVK gravitational wave detectors. So please welcome Chung-hee Dong.
Introduction. Today, I'll tell you about new ways that we can look into the dark matter using gravitational wave detectors, formerly known as LVK, that's LIGO, Virgo, Kagra. Now they changed their name. It's International Gravitational Wave Network. So let me begin from the introduction. Okay. This is a one-page summary of our physical cosmos. So we know from the various observations in the past 10 years or 20 years that our universe is spatially flat and expansion is accelerating. That statement is coming from this pie chart from Einstein's theory of gravity. So we know that 45% is the atom, 23% dark matter, and 72% dark energy. Dark energy is responsible for cosmic acceleration. And dark matter is another name for the excess amount of gravity. We don't know yet if it's still matter or some misunderstanding in gravity sector, but I'll call this as dark matter. And in this talk, I'll tell you about the model that we have for dark matter that can change, that can make the new signature in gravitational wave detectors. So this is the guest of honor today. We are not completely blunt about the nature of dark matter. There are a couple of hints that we have about the nature of dark matter. First of that I know is that dark matter is not baryonic. The evidence is coming from cosmic microwave background. This is the CMB power spectrum of temperature fluctuation. This is another way of looking at the hot and cold spots in CMB. Y-axis is the fluctuation amplitude. You can think of that as an RMS of the fluctuation. X-axis is angular scale. You can think of that as a scale in which you can smooth the CMB anisotropy. So you smooth the CMB anisotropy to 1 degree filter, for example, then the fluctuation amplitude is about 1,000 microkelvin squared, which means that fluctuation amplitude is about 30 microkelvin. Square root of 1,000 is about 30. And you all know that the temperature anisotropy is 2.7 Kelvin. You take the ratio, 30 microkelvin over 2.7 Kelvin is 10 to the negative 5. That's a level of fluctuation carved in the CMB that you observe from Planck and WMF satellite. Combining this fact with the result of the cosmological linear perturbation theory, where density perturbation can grow only by proportional to the scale factor. CMB happens at redshift 1,000, means the scale factor at CMB time is 1 part in 1,000. So 10 to the negative 5 fluctuation can only grow by a factor of 1,000, which gives us 1% on the scale of Galois cluster. Without dark matter, we cannot even form Galois clusters, which means that dark matter must be completely secluded from baryon and photon because this fluctuation is carved from the baryon-photon interaction. They must independently grow in time, and their amplitude must be much larger at the CMB time. Therefore, their dark matter is not baryonic, means that it cannot interact at all with photon. Okay. Second piece of evidence is coming from Galois cluster. This is one of the famous picture of two colliding clusters.
Understood in the previous page, what is the relation? So galaxy cluster scale has bigger.
Galois cluster, if this is all we have as a fluctuation, on Galois cluster scale, we only have delta rho over rho 1%. So we cannot, which is inconsistent. It means that we cannot form Galois cluster So we need to have another source of fluctuation besides baryon photon fluid, which is dark matter.
So this is at the time of decoupling.
Yes, write it down.
And at that time, what should be the galaxy cluster scale fluctuation?
It's about, it should be more than 0.1%. Because it cluster scale fluctuation right now, we measure is order 1, not 10 to negative 2.
So to grow to order
Yeah.
1, it should be much bigger than 0.1.
That's right. The lesson is that baryon cannot couple the dark, or dark matter cannot couple the baryon.
And what you showed is the fluctuation in the scale.
Right. That angular scale is also multiple moment. So I just took the reciprocal of multiple moment, call this a scale.
It's essentially the same as anisotropy.
Yeah, so the angular power spectrum, this is angular power spectrum. Yeah, I just interpret the angular power spectrum in slightly different way. Good? Yeah, please stop me and ask questions. So this is a two colliding cluster. How do you know that? Because of this chart. So this big cluster and small cluster is like a bullet passing through. That's the speed that we see. And reddish color, pink color is the distribution of gas. Gas particles, they interact very vigorously. Therefore, when two gas particles collide, you see this kind of structure and they are stalled in the middle. On the other hand, the galaxy is here and galaxy is there. And the blue color is the distribution of dark matter or the mass, bulk of the mass. So mass distribution is far from the gas distribution. That gives us one hint that dark matter are extremely non-interactive among themselves. And we measure the offset between the galaxy center and dark matter center, and that can give us the hint for the self-interaction cross-section of dark matter. From this measurement, we know that self-interaction cross-section of dark matter must be bounded from above, must be smaller than 1 centimeter square per spot. That's another piece of evidence about that. That's it from the astrophysics. And then particle theorists, they are hoping to find the signature of dark matter by this diagram. Two dark matter interact, we create a two-signal model particles. Depending on how you look at this diagram or how you attach the time direction, this one diagram can be interpreted in 3 different ways. Most famous example is called the WIMP miracle. Early on, if dark matter interacted with the model particle, its number density must be very large when temperature of universe exceeds its mass. Because essentially, any photon in the universe can create dark matter particles. Right? But then, as temperature drops, the high temperature and low temperature, as temperature drops below the mass of dark matter, mx, its number density drops, and interaction rate drops. At some point, dark matter particle must be coupled from the thermal bath of photon or the baryons. Right? As they interact much stronger, they can stay in the equilibrium. This is the equilibrium, famous Boltzmann suppressed vector. If the interaction rate, the gamma is sigma v, if the interaction cross-section is large, they remain in thermal equilibrium until later time. They have lower number density. If interaction rate is low, they decouple quite earlier and they have higher number density. That's one way that you can estimate the dark matter number density or the energy density in the thermally produced dark matter. This is a calculation first done by Lee and Weinberg. And then this calculation led us to this WIMP miracle. You find the particle theory parameters on the right-hand side. Without further ado, if you just plug in some interaction scale, we get the cosmological number of 0.1. That's the motivation behind the WIMP dark matter particle. in all the universe. And in order for this thing to happen, we have to have two documented particles create the single model particle. And we can ask ourselves, is this happening right now?
Why you chose 0.1?
0.1, because the observed value of omega matter 0.2 h squared is about 0.1.
For historical reason, H is 0.7.
Right.
Question 2 is the
H is
Yeah,
just
7 squared times 0.2. Yes.
this H square. We should remove it.
Right. And then people can look for the same signature in the gamma rays. And this is a map of the gamma ray sky measured by Fermi Gamma Ray Telescope. And here I spotted a couple of dots. The places for dwarf galaxies. And we know that dwarf galaxies are dominated by dark matter. Their number density is high. So if dark matter interaction happens, the most conservative candidate is the place for dwarf galaxies. Right? And what they did was they stacked around the gamma ray sky signal around dwarf galaxy, which is the solid line, and they compared that with 300 random pointings. That's dashed lines. If there were signature of dark matter annihilation, we expect to have an excess of gamma ray at the position of dwarf galaxies. But as you can see there, random pointings are consistent with the dwarf galaxy position. So we didn't see the evidence of dark matter interaction in the gamma ray sky.
So can you explain what is the meaning of random pointing? So I understand that you can compare the emission from the.
So we're comparing the likely place to see dark matter emission, which is dwarf galaxy,
So you
against a random point. It's just a random.
Yeah, they have to point at the galaxy at the dwarf galaxy.
Right. So you have to compare that to the baseline.
Yeah.
Our baseline is just random pointing, not galaxy center, of course. Some random pointing, non-dwarf galaxy.
How to compare against the background? Let's say.
Yeah, that's right. Yes.
Okay.
How good is the localization in the gamma rays? Like, can you actually?
I think it's pretty good. Yeah, yeah.
That you sort of say it's in the direction of that bigger.
It looks pretty nice. Yeah, it's localization for gamma.
Another question is that for the exclusion product that you have shown, is it only for S-wave type of dark matter annihilation, right? Because
Yeah, of course.
Yeah, of course. Yeah.
Anyway, this is a recent estimation.
That's 2015.
2015.
Yeah.
So 15 dwarf galaxies, but when the date? Because
That's something at all.
20, so 10 years ago.
Yeah.
Because PB bar
I think that's the most.
excludes below 100 already reaches the
Which one?
So the exclusion, this plot, if you look at the plot, PB bar, the wind miracle, which is 3 × 10⁻26, is already excluded for a mass below 100 eV. I'm not completely sure. Probably there are some systematic stages.
Yeah, the expert things.
Yeah.
That's enough.
No, that's why I said because this plot seems quite aggressive.
Yeah. Okay, and then you can also find a direct detection signature. That's like what people do for the document search experiment. You prepare extremely non-interactive material, put it in the ground, wait. Right? Tone times time. That's their figure of merit. And look at that. I think this is the most up-to-date most sophisticated version, the LV, Lux and Zeppelin, 2025. We're almost hitting the something called neutrino fog.
There's something neutrino floor, and now it's become the neutrino fog. Fog is
That's what people say. Yeah, I think I got it from the
So they
PDT.
through the floor to the fog.
So the idea is that if you in the future you can use this directionality.
Oh, in the most
You can live in the frog.
a bit positive way.
Right. It's yeah.
So they try to be more positive.
Yeah, but I call it endpoint of verification. So we're very near about 1 order of magnitude.
Yeah, of course, this assumes a specific type of interaction.
And all the neutrino detectors will turn themselves into, all the dark matter detectors will turn themselves into neutrino detectors.
Yeah,
Very
quite
soon.
expensive.
So that's the status. Today I'll tell you about the new way, because I have a new toy or a new detector, gravitational-wave observatories. This is a picture of Livingston, Hanford, two US-based LIGO detectors, and Virgo is in Italy, in Pisa. With Cagra, they form international gravitational-wave network. Why am I telling you about this? We have so many detected sources of gravitational waves. This is the holy grail kind of what they made. The three fascinating name graveyard, and those are all black hole binaries that we have detected so far. And these are X-ray binary, that's neutron star, and those are black. And I'm asking a question about the mass ranges below 1.4 solar mass.
Below the mass, which are coming to come down.
That's right. That's the point here. So, do we have some sources here? Why don't we have some gravitational wave sources here? I mean, it seems like we have some. I'll tell the story about that.
So I mean, you don't observe any merger or any
So far.
so far?
But is that because our instrument is not sensitive? No, that's not. I'm showing you as a function of frequency, something called the power spectral density. As you can think of that as a gravitational wave amplitude. I'm plotting here three different curves, three noise curves. Red line here is noise curve for advanced LIGO now means as of 2018. I think we are in between red and magenta. Magenta is advanced LIGO after it's full of potential. These are noise curves. And this is a noise curve for the Einstein telescope. It's the 40-kilometer monster gravitational wave detector we are preparing for it. Compared to noise curve, I plotted three different signal curves. This is a 10 solar mass binary at Andromeda. This is 0.1 solar mass, a 1 solar mass binary in Andromeda. This is 0.1 solar mass binary in Andromeda. Our detectors are completely capable of detecting those. Where are they? That's a question.
Maybe they're just irregular, right? I mean, if you wouldn't bright siren event we had was at 40 megaparsecs, right?
They're neutron stars, right?
Yeah,
right.
I've only seen one in 10 years.
And the caveat is that because I'm talking about the smaller black holes, less than Chandrasekhar mass, we can only reach to certain distance. As a function of component mass, the equal mass binary.
Previous page.
Yeah.
So does it mean that since you have roughly in the Andromeda distance, let's say, solar mass or even smaller than that, but the noise curve is much lower.
Yeah.
So if there exist sources, there's a possibility
Yeah.
it should be seen.
Yeah.
That's what
Yeah. Our detector as of now is completely capable of detecting those sources. And that's my main target.
Why have some kind of broadband? I mean, are you showing some looking at the gravitational wave from all these spiral base or because
because they are small black holes, their ISCO frequency is much higher.
right? So
You can go all the way down. I think this 10 solar mass must stop somewhere, but the 1 solar mass and 0.1 solar mass, they should extend.
so you have this line is meant for before the ISCO.
Yeah.
And you have these spiral base that have gravitational waves in that shape, and ISCO will give you much higher signal, but it will be much higher.
That's right. Let's talk about this very brave plot. One solar mass, 1.1 solar mass binary, you can go all the way to 100 megaparsec. And 10% of solar mass, we can go to Virgo cluster. And 1% of solar mass, Andromeda. Right? So these black holes, if exist, we can hear them from the current LIGO detectors. That's the motivation. But then why do we not talk about this sub-solar mass range much? There's a reason. I think we already have a keyword, Chandrasekhar mass. This is as a function of circumference or the diameter of the stellar object. Y-axis is their mass. And this is the histogram, the diagram for the stability. So under this curve is something. Let's say we have solar mass star at the end of its life cycle, exhausted all the fuel, and it will collapse until it hit the white dwarf boundary. The solar mass star will be white dwarf. Procyon is 2 solar mass, assuming there's no mass loss due to some stellar wind, will collapse until it becomes a neutron star. And Sirius is about like 2 solar mass, and it will be a black hole. It's kind of easy matching problem. So normally for the star born below 8 solar mass will be a white dwarf. Between 8 and 30 solar mass will be a neutron star. Above 30 solar mass, it will be a black hole. And this peak here, that defines Chandrasekhar mass of 1.4 solar mass. That is the maximum mass that any neutron star can hold itself against the gravity by using the electron degenerate pressure. White dwarf, sorry. And neutron star has a little bit higher mass. It's between 2 and 3 solar mass, because neutron star use the degenerate pressure from neutron instead of electrons. Okay. And if you think about the origin of this Chandrasekhar mass, this is one of the key equations of this stuff. This Chandrasekhar mass is a combination of 2 parameters. Parametrically, is the Planck mass cube over proton mass square. If you plug in numbers, it will be a solar mass magically, right? So there are 3 places in all of physics I know which involve Planck scale: Hawking radiation, primordial gravitational wave, and Chandrasekhar mass. Unlike Hawking radiation or gravitational wave, Chandrasekhar mass happens all the time around us. The rationale is that for a given mass of stellar object, number of electrons is inversely proportional to the proton mass. If you assume the charge neutrality, that's why this dependence comes about. And the observation is that Planck mass is a fundamental constant of nature, but proton mass is not so fundamental. It's given by QCD. Okay? So if dark sector has some different proton mass, what will happen? If dark proton mass is 10 JeV instead of 1 JeV, Chandrasekhar mass will be 0.1% of solar mass. Then you can create those black holes much lighter than what it can generate from the stellar evolution. That's the idea. Right? So the minimal setup that I'm thinking about is this passive dark matter. This passive here means the dark matter that are allowed to lose their kinetic energy. Instead of thinking about one boring dark matter species, we can think about some variety of dark matter particles: dark X particle, like dark proton analog, dark C particle, dark electron analog, and dark ENF. That's a minimum setup to allow energy dissipation and to use something that I know as an astrophysicist. The process is I can apply the same kind of ENM process. And here there are 4 parameters: dark proton mass and dark electron mass. So here dark proton doesn't have to be a composite particle. What I just require is charge neutrality and one particle being heavier than another. And there could be dark ENM. There are parameters: proton mass and electron mass and coupling constant and the temperature of dark radiation compared to our CMB radiation. There are 4 parameters now. Right? Cool. Sorry, it's fast. I have to use one. Any questions? Yes.
Why do you use photon mass, not neutron mass?
Oh, I just think of them as equal mass. Proton, I mean, they're very
Because it's
similar.
charged and that is that.
Yeah, neutron there's no charge. So I don't need.
Oh, I see.
this is-
Dark proton is charged.
Yeah.
Electromagnetic, not electromagnetic.
It's a dark radiation.
dark radiation, dark ENM.
Dark ENM, okay.
It's a alpha D means the dark ENM. Although I just use the same fine structure constant, it's a dark ENM.
And you need the proton because of the formula, is that it? We just saw.
I just need some.
Could you replace it by a dark neutron? Let's forget about everything else.
No, but then there's the charge. If there's a net charge, then yeah. I need charge neutrality, and I also need the mass hierarchy as well. Just to use the same formula that I have in astrophysics.
I can understand, you can just introduce this at X and C alpha D. So what do you mean by this temperature?
Oh, because it's the cosmological requirement. Because I cannot add some arbitrary amount of radiation because that can affect our background expansion.
So that is designed to fix the radiation coming from your dark.
Yeah. And then this C should be constrained to stay below the effective neutrino species.
So these particles interact among themselves, but they're completely secluded from.
That's the setup,
But
yeah.
they have it gravitational effect. Yeah. And what is the dark matter? X or C? Yes, the
They
combination.
both dark matter. So why do I need that? I need that at the beginning, I started the talk by saying that I want to create black holes, right? Then now I suddenly tell you that I need some energy dissipation. This is one picture why they are connecting. So at the beginning of universe, when when everything starts to collapse, we have CDM, the blue, and baryon, they are all coming together to have a big giant halo. But at the end of that, what happens? Baryons, they sink toward the center, they form galaxy. But dark matter is still sitting out there, and then this is a form of halo. Yeah.
They cannot be interacting, they have two different temperatures. The cold dark matter has one temperature, and so here you are talking, this is just baryons.
Yeah, this is a baryon. I'm just telling you some example why I need energy dissipation, right? And the difference, what baryons do and what dark matter do not do is energy dissipation, right? So what happens is that baryons, they dissipate their kinetic energy, means that we can see baryons by the light that they're emitting, right? The energy that is carried out by the light is lost from their kinetic energy. And then if they lose kinetic energy, they sink towards the center of the gravitational potential, and then they form a galaxy. That's the process that I want to mimic.
The story looks like the conventional formation of black hole. So we react through the radiating for the formation of black hole.
But this is the standard.
The standard scenario, but I want some portion of dark matter to do the same.
To
form dark matter black hole.
So the galaxy is the usual method.
Yeah, usual variant.
And what is the difference from the typical?
CDM cannot collapse because they don't have channel to dissipate energy. But if I have this structure, they can dissipate energy because they can radiate dark radiation, and then they can form dark black hole.
You need some additional ingredients to form halo beyond what you just did. You need some more ingredients to form the halo beyond what you just did.
No, I think this is a minimum setup. Why do you think I need more?
Because I mean they will interact strongly and they will form some structure. You still need some halo.
All right, I need halo as large as 10 to 11 solar mass. I think I'll tell you how I do that. All right, this is not my original model. Lisa Randall has the same model. She called this atomic dark matter model. She even killed dinosaurs with her model. Right? What she made is it's called the dark matter and dinosaurs. What's the connection here? So she created, she made an exactly similar kind of model, but at a different corner of parameter space. In her model, dark matter can dissipate the energy so strongly, so she expects to have some thin disk in our galactic plane. And then you know that our solar system is orbiting around the galactic plane, but then we are not orbiting on the plane, we are wobbling up and down. This period is about millions of years, and we pass the galactic center, there will be anomalous gravitational interaction that increase the number of comets and number of the dangerous materials that can kill dinosaurs. That's her model. But in her model, though, she introduced the too strong electromagnetic interaction. So if, there's something similar to CMB must have happened in this world, in this dark world. In that case, just like we have this black line, our baryon acoustic oscillation, in her model, we expect a second acoustic oscillation in dark matter center, which we didn't see. Her model was killed by not seeing this second bump in galaxy power spectrum. But the reason here is that because in her model, in this dark matter model, the dark recombination, just like CMB recombination, happens close to redshift 1000. That's wrong. So I should avoid that. So in my model, we push the dark recombination way earlier. So dark recombination in my model happens redshift 100,000. In this case, dark acoustic oscillation disappear, or it happens on very, very small scale. That's the way that I can avoid that constraint. So this is one example of a proton of 16 JeV, that electron of 140 kV, and then recombination happens like 51,000. So dark acoustic oscillation happens very small scale.
We know how long it's going to take to observe dark acoustic oscillations. Maybe in general, like even observationally, like.
Oh, if this DAO is 0.02 megaparsec, that happens way smaller scale than Lyman alpha forest. I don't think we can.
Is it even possible? But technically, would it take a century? Would it take? How long would it take? No, for this model. Just
for this model?
No, in general, for any, let's say, dark acoustic oscillation.
So dark acoustic oscillation must curve the exactly same oscillation on top of the normal acoustic oscillation. If it happens near redshift 1000, we could have detected it already. It's all about where it happened.
Okay. Then we're looking for it. Like statistically, how would you go about this?
I think this paper is from Francis Yan. He might have done it. All right. And second thing is answering the Sungwoo's question. I want this thing, energy dissipation, happens for just to create black holes. But I know that around our galaxy, around those big galaxies, we do have galactic halo. So I need somehow make dark matter halo for the large galaxies, but break those halos for small galaxies. How do I do that? Everything is controlled by one number. It's called the cooling time. Cooling time is a time scale within which the halo, dark matter halo, can lose enough kinetic energy. If cooling time is greater than the age of universe for those big halos, and that those big halos still exist, the small halo, they collapse. That's the idea. And this is a paper by, I think, Berkeley, and they have some parametric way of importing this condition. It's called the Reed oscillator.
Is the age of universe?
Age of universe, yes.
How to?
10 billion years. We have 13.6 billion years, right?
It means dark matter exists before the.
Oh, yeah, that's the most conservative condition, yes. But if this cooling time is how much does it take to lose energy? The total kinetic energy is proportional to number density.
Anyway, it eventually lose the energy and then eventually
Collapse.
It becomes collapsed black hole.
Yeah.
But the black hole exists here, but actually T age is like T. So
I want this condition for the halo mass greater than 10 to 11 somehow. for the halo mass lighter than 10 to 11 solar mass, this inequality is opposite. And then for those small halos, cooling can happen efficiently. For large halos, cooling cannot happen efficiently. The reason is that energy dissipation happens in proportion to n squared because it's two-body interaction. Total energy is proportional to n. The cooling time depends the density. Right? So that's the way.
So you have very, dark matter, which has been decoupled very much earlier than the usual matter. So they are kind of neutral in the dark photon, right? So then when you say the dissipating the energy, you mean by so getting shrunken by gravity, then they are just getting away the kinetic energy.
Yeah.
Or
They send off the dark photons. Their kinetic energy is dissipated by the photons.
So
And
the way of doing is that function end up.
They are floating around the universe.
Yeah, so
They're not doing anything.
bounce and then
That's right, yeah. But in our setup, we set the EPR to push the dark recombination to earlier time. Dark photon has to be much cooler than single photon. So it exists, but doesn't do much.
since it's dark matter already is neutral in dark photon.
Right.
Just some acceleration, collapsing will not radiate any dark photon.
That's true.
Radium.
Yes, but when they are formed in the plasma state.
It's very, very early.
Yeah, very early. That's the thing that I need to form this thing. Current generation dark matter, they are doing nothing. They're the atomic state. Yeah. That's another way of thinking about that, basically. Okay, but then because I don't want to do this complicated simulation, I just use two mass scales. First thing is already the top. I told you 100 mass scale, which is proportional to 1 over mass of proton square. Second mass scale is important for the population 3 star formation. If you think about the population 3 star, which is the star formed out of pristine gas, which is basically hydrogen and helium, the formation of star in that environment is exactly parallel to the formation of dark matter star. So in that case, there's opacity limit is done by Lindenberg and Martin Rees, and there's a mass scale, minimum mass scale of top 3 star, just coming out of the adiabatic cooling of the gravitational collapse. So top 3 star has 1,000 solar mass. This kind of mass scale of top 3 star, but if you can increase the dark matter proton mass, it can be dropped. And also if you decrease the temperature, it can be dropped too. So to reduce the mass of dark matter star, what I did, and because this temperature of the first object is determined by the energy level in dark, our top 3 star is determined by the molecular low vibration energy gap. And that is inversely proportional to the moment of inertia, which is 1 over mass of proton and the size of atom square. If you remember the quantum mechanics class, the R of hydrogen atom is proportional to 1 over electron mass and then finds as a constant. That's what it is. Yeah.
So then the temperature you are talking about is Z is much larger than 10 to the 5 in the dark matter state. Right?
Or this is the temperature of the individual collapsed object.
Oh, it's not the global.
It's not global temperature, right? There's a temperature. It's a how low temperature can you achieve by using various cooling channels. The lowest temperature you can achieve for the top 3 star is the first ground from ground state, the first excited state of the hydrogen molecule.
So it can be much cooler than the surrounding dark matter
Yeah,
temperature.
because it's a runaway process. As you start the collapsing, you increase the number density. If you increase the number density, you increase the interaction rate, and then you more efficiently you can lose energy. So it's hard to initiate the collapse. But once you initiate the collapse, you can form slump. And I have one plot to show. And for the Popsy star, 512 Kelvin is the minimum temperature that molecular cooling can let us. For us, if you increase the mass of proton and adjust the mass of electron, you can lower this number as well. So after that, we use the result of the population 3 binary literature, and then we just rescale them by using this mass ratio. For example, for these 4 different proton masses, that is 200 JeV to 50 JeV, I can plot the mass spectrum of dark matter black holes coming out of this process. And this power is coming from population 3 star. And from there, I can also compute the church mass. Church mass is this funny combination of mass ratio and the total mass. That is one parameter that determines the amplitude of gravitational waves. And church mass, and then horizon radius. This advanced LIGO as of 2018. There's a full upgrade. That's the other way. Advanced LIGO 2018, full upgrade, and there's Einstein telescope. For 10% of solar mass, you can go to say 10 megaparsec. That's the distance of the roller coaster. And that is the distribution. I think my gravitational wave colleagues asked me to plot this. So if I plot this, then they can turn that into a constraint immediately. So you made one plot.
So I don't understand the vertical axis.
Yeah, this is the horizon radius. So for a given church mass, how far can you go out to search for this object? 10 megaparsec, 100 megaparsec. The horizon radius in the gravitational wave literature is determined by A sigma detection delay. So this is a table. I normally don't put table in my talk, but this number that I want to highlight is that even the current LIGO, advanced LIGO, and then LIGO full upgrade, we expect to have between 1 and 1,000 event if the matter mass is 16 JeV and the electron mass is 144 keV. We have this range of numbers because just like not every baryon in our universe is locked into star, not every dark matter must be in black hole, right? So we have this free parameter called the total rate, the fraction of black hole, a fraction of dark matter in black hole between 10 to the negative 5 to 10 to the negative 3.
This number you set or you can estimate? So
I start with the literature. It's a kind of range that we have some educated guess. I mean, this
is a free parameter.
Yes, free parameter. Yeah, but it depends on the environment. I think this is the in void area. That's a cluster area. The fractional variance locked into star.
Taken values from our star.
Yeah,
it seems just extrapolate.
That's kind of my guess. The fraction must remain the same because once you form some collapsed object, the evolution must be similar. All right, so let me give you some example. So this is the whole glad again. So these two are the famous example called the GW17 or A17. Do you know this event? That event turns out to be the kilonova, and after the LIGO detection, we also saw the Fermi and the integral, the gamma ray detections, right? With the 1.7 second lag. But that was nice. But then what about this one? This one. These two. It's a GW190425. In terms of mass range, one of them is lighter than 1.4 solar mass. We did not see any E&M counterpart. And that's also an oddball. The first mass is this range, the second mass is that range. You could be either a binary neutron star, neutron star black hole, or black hole, black hole. If it were binary neutron star, they're very weird. This is that system. Total mass of that system, 190425. And if you combine, oh no, sorry, this is that system. And if you combine the stat of all the binary neutron stars we have in our galaxy is there. There are 5 sigma away. Of course, to be fair, it is electromagnetically selective neutron star binary. That's gravitational wave selective neutron star binary. To be fair, but this is weird too. It's intriguing. And can they be the primordial black hole binary? That's my favorite slide. Because the primordial black hole can have any mass, right? But if you are to create primordial black hole of that mass range, you must have large primordial curvature perturbation on that scale, right? That large primordial curvature perturbation will generate induced gravitational waves. For those of you who were in Sihung last month, you saw me talking about induced gravitational wave. The reason was I was thinking about this problem. And they computed the amount of induced gravitational wave generated by the large stellar perturbation that would generate a primordial black hole of 10% of solar mass, 1% solar mass. They must have produced the gravitational wave, which is detectable by nanograph, the Porta timing array. By non-detection of nanograph in 11 years, we have strong bound for the primordial black holes. So it cannot be primordial black holes. So then I went one step further. What if this 190425 were my guy? Small black hole. What's the implication of having that in our bucket? This one gravitational wave event, if I were to interpret this as a black hole come out of dark matter, I can immediately set the limit of the proton mass must be larger than 1 GeV. Because its black hole mass must be smaller than 1.4 solar mass. Of course, if there's a perfectly fine possibility that this thing is not my black hole, in that case, I have a limit. That's what my colleagues in LIGO liked. So in the official paper, I was collaborating with the LVK collaboration for these 3 papers. For the O3A, O3, and that is O4A. We only have a limit as a function of minimum mass of the dark black hole was a fraction of black hole in total dark matter. Okay, so you can constrain between 4 to 5, 4 to 5, and now it's 4 to 5 is almost hitting the 5 at 1 solar mass.
This fraction with respect to the total dark matter or the
Total dark matter.
these particles, the dissipative particles that are not in black holes.
So here we assume that 100% of dark matter are particles are dissipative. And what's the fraction of black hole inside of that dark matter?
You can allow 100%.
So still allowed. I didn't say any
100% dissipative dark matter.
because it didn't violate anything.
Yeah, because it's completely dark.
It's fine. If the temperature is so low, then there's no other bound that is allowed.
In other words, you can do that, but you have no way to detect it in any way.
This is the way.
Yes, but
yeah, that's right. Other than this, yes. I understand what I think.
It's a crazy number of authors on these papers, right? A crazy number of authors on these papers. 2605, 0.
Yeah, they're all LVK plus me. I think after 03,
Did you get first ownership on this?
I got the last offer. So they stopped.
Looking at all the names here.
They stopped making MOU with individual.
Oh, you did. Oh, Shandera and John.
Yeah. The very last page.
And Black. Who drew Black then?
We are not part of LVK collaboration. We got into it by MOU. So
Okay. So Black, Shandera, and John.
right. All right. It all depends on the cooling functions. How efficiently can you lose energy as a function of your quantum state? As you increase your temperature, you increase the number of free electrons, free dark electrons. As you decrease the temperature, you're losing number of free electrons, and at some point you're completely neutral, as Tom said. But then we can also add molecules, and you can extend this graph. Yeah, this is a standard plot. So if I want to simulate this thing, so what I did with my students is to revisit molecular chemistry. We computed all the cooling channels as a function of the mass of proton, mass of electron, Planck's the constant, and those things. And we did that in preparation for the running cosmological simulation of dark black hole formation. That's what I'm preparing for. And these are the phase space diagram as a function of number, density, and temperature. This is either very cooling and collapsing. You increase temperature either collapsing, but as you increase the temperature, you also increase number density. As you increase the number density, you start to cool, turn around, and then you can make the cooling down to say 512 Kelvin. That's the standard case. For that case, you can even lower this even further. So that's what I meant by it's hard to bend this curve, but once you bend this curve, and you can make the run-up collapse until your energy dissipation is very inefficient. Because you're too dense, then you start to be opaque to radiation, then you increase the temperature again. That's what happened in the star formation as well. Yes, it's a boring astrophysics, but I just show you that I have some machinery and that's ready. And another question, I told you about the fermionic formula, where the Chandrasekhar mass is proportional to 1 over proton mass square. What about bosons? Can bosons make black hole? That's this slide. For bosons, we have another constraint. What I can do is very simple-minded calculation that Compton length of this bosonic particle is smaller than Schwarz's radius. Then it will be a black hole, right? The constraint is that the bosonic Chandrasekhar mass is Planck mass square over the particle mass. If bosonic particle is 10 to negative 10 electron volt, it's kind of the super radiance kind of boson scale, and you can form a solar mass black hole. It's kind of cute. But if you have some bosonic particle, then you know how to make the solitonic structure. And if the solitonic radius is smaller than the Chandrasekhar mass, you can form small black hole. There's another channel. But I don't know how to make a cosmologically viable scenario with this thing yet. And also, this is the result that I have to solve the Schrödinger-Poisson system. It forms a black hole when the radius is 1/3 of Schwarz's radius. Obviously, I cannot apply the Schrödinger-Poisson system here, and I have to use a full GR. So I'm now using the sophisticated what's called GR Chombo kind of numerical simulation to simulate this system. That's another interesting side project. Oh, and also, this is all done by the mass range. This is my most recent paper, posted this last month. What about the white dwarf black hole system? If you have white dwarf, like 1 solar mass, white dwarf and heavy black hole, so 0.8 solar mass and 5 solar mass, can they mimic the signal, right? Answer is no. And this is a very interesting system. As a function of frequency, this is the gravitational wave strength, how they evolve. At first, these two systems get getting closer to each other, and frequency increases. But then, white dwarf is a big size. 1 solar mass white dwarf is as big as the Earth. And the materials in white dwarf radius fall into something called a Roche-Rho. It's like a first Lagrange point between, if you have ever solved the three-body problem. And this is the channel opened up for the mass transfer between white dwarf and the black hole. So mass starts to transfer from white dwarf to black hole, and then the mass range changes, but they get closer and closer and closer by radiative reaction. But at some point, they get further away, further and further away. They refuse to collapse. So they get closer, and then they go further. That's the signal. And then in terms of the signal noise curve, this is a noise curve for LIGO and cosmic explorer and Einstein telescope. This system will generate signal here. On the other hand, my system can go all the way to big high frequency. So we can clearly distinguish between white dwarf black hole system to small black hole system. So that's not a problem.
So what is the main physics that prevents white hole cannot not too close
Yeah.
up? Why?
Mass transfer. There's a mass transfer happens. So if you transfer mass, there's you can set up an equation for the radius. There are two competing vectors. The radiative reaction means that you emit the gravitational wave and you lose energy, therefore they get closer. And then if you transfer enough mass, and then the scapular motion prefers have low energy when they are separated increases. So that's a known factor for the two-body interactions. The Kepler problem with the varying mass, that's a very interesting classical physics problem. If you transfer one mass to another, then they'll move away. Oh, and this is my favorite part. So one day I got text from Kumon Kang, who was monitoring the gravitational wave detector. And he said, "Oh, Donghi, you have good news." What? And then it happened in the August 18 last year. So that's this event. The fake chance false alarm rate is 1 in 5 months. And its localization is here. And they have the designation called the GSTLR. That's the pipeline developed by Penn State colleagues. It's called SSM, subsolar mass, right? I was very excited. And indeed, its probability distribution for the source frame church mass is between 0.1 and 0.8. Oh. And then they also have the alert thing that, and there's also the Zwicky transient factory observation in the same kind of area. So they could have some UNS signal, but it was fake alarm. And also this signal didn't last long. After Kumon sent me email, and then I go to my colleague at Penn State, and they said, "Oh no, this signal went away." I lost my Nobel Prize.
Once you get down to these rates being so low, like once in every 5 months, does LIGO take these things seriously? Like what usually is the threshold for?
Oh, there's ridiculous number.
Hundreds or
I don't know. It's more than
0.
more than digit, right? More than many digits. So there's a public alert for this. I was excited for about 1 hour. So I think now you all agree that gravitational wave provides an exciting new avenue for detecting a new kind of dark matter, right? If the dark matter proton exists, if they can dissipate the energy, but the proton mass is much heavier than GeV, they can make small black hole, right? So, and for example, if this guy, the 190425, were a dark black hole, you can immediately set the mass limit for dark proton mass. And official verdict for this one is the null detection. But the 2508-18 was quite interesting. Hopefully, there are colder system ready to collide soon. I'm just waiting for this. And this is interesting way of looking at dark matter. And then my group and my students and Sarah's student now, we are ready for running the full cosmological simulation of the formation of this black hole. So, but still, the hint is too low, so I'm not devoting 100% of my time. But once I promised to my colleagues that once they have some stronger hint, I'll devote all my research time to this small black hole. All right, thank you very much.
Very much for the nice talks. So now we have a Q&A session. So please raise your hand if you have any questions.
So LIGO must be, if we go back to the plot with all the masses, stellar graveyard, etc. LIGO must be doing a whole lot of searches with templates in the in the range that interests you. What are the best candidates? What are the candidates that LIGO thinks?
For this one?
No, in general. Like, what would LIGO think is the most likely thing that would come out of that low mass range? Is it this?
I don't know. They don't know. That's why for the solar mass range we have a little bit sparser searching grid, because as you know, the LIGO is using the matching filter. So we have to prepare some matching filter for individual event. So we're using that at the moment. But I'm now preparing for doing something else, because we are here. Normally we will see the signal from here, very far away from East Coast, right? So I think GR effect in this region at least will be quite minor. So I'm determined to look at this signal just using the Newtonian physics and some 2.5 PN, like radiative reaction. That could be possible without using the matching filter. That's something I can do. I'm set up to do that with the help of cloud and codecs.
So let's say if you see, let's say, see the signal coming from the solar mass, then whether it is from this dark matter model or from primordial black holes, how can you distinguish?
I think primordial black hole channel is gone by now because of this plot. So primordial black hole coming out of standard inflexible perturbation must generate the gravitational waves in PTA band, pulsar timing array. But up to 11 years of accumulation of data, they didn't see anything. So there's a bound of the fraction, 90% bound for the fraction of dark matter black hole as a function of solar mass, PBH. And I think this, for the one solar mass, is already 10 to -7. So I think it's pretty safe that.
Quite impressive, 10 to -22.
Yeah. So it's pretty safe to say that primordial black hole cannot be the subsolar mass range.
Could it be systematics in this plot? Like, how strong is this?
I don't know how much
do we have multiple PTA experiments, or is it just one?
There are nanograph in the US. There's a park in Australia and the Europeans and India.
And do we all have an analogous plot for all of these guys? Like, how strong? You'd like to see this plot from
I have no answer for
all
that question.
collaborations.
But I think at least I want to check their calculation. That's why I asked this question to CP when he gave a talk in CP. But I think this plot is so low, these numbers.
This plot is known.
So that depends on, because they have their sensitivity curve as a.
Yeah, but it's suspicious. This curve is 10 to -22. It's so noisy. I honestly, common sense would tell me look into that.
Yeah. That's one of my.
Let's say, so for the pulsar timing array PTA the data, since it is really some stochastic background of the gravitational waves, then let me ask whether it can be from dark matter.
Dark matter means that.
Your model.
Oh, my model. Yeah, depending on which ratio you're looking at, right? But then the frequency range of PTA is nanohertz. So if you are to create nanohertz, you either have a circular black hole, circular supermassive black hole, or primordial black holes gravitational wave redshifted to that frequency range.
What I have in mind is very confusing and interesting things. We have some the standard model sector. You have copy of some essential copy of that in the dark matter sector. So whatever you say in one sector, so of course all the values like photon mass or the values may be different.
Right.
So if you say something here, then I'd like. What happened then in this case and vice versa? That's why I'm asking.
Right.
And since you said PTA data is the main thing that rules out the subsolar mass source as a PBH, but it is okay for the dark matter.
Right, because
What's the major
the
difference?
reason between that is the reason why they constrain PBH is because PBH can only be generated in the large fluctuation in the primordial universe. That large fluctuation in the primordial universe will generate the gravitational wave, and they at early on, and they are redshifted to the PTA band.
Yeah.
Nanohertz is like one oscillation in 10 years. It's a very, very low frequency. So, but then instead of that, my black holes are formed later universe. So they are only redshifted normally, not by a factor of 10 to 10.
So yeah, in other words, in this model, so can you repeat again the progenitors of this wave, the stars? When do they form?
They form around redshift 20 to 10.
So it's similar to the
For top three, yeah, top three star.
The James Webb can look into that.
If they can only, if only they can see the dark radiation.
No, but they are basically looking at population 3 stars, the first population stars.
Right.
So they could be. So you mean that there could be a mixture of ordinary stars and
ordinary stars that radiate the usual photon,
yes,
and dark stars that radiate the dark radiation, which yes.
But in this scenario, still I'm confused. You are assuming that this dark proton and dark electron, they provide which fraction of the dark matter?
100%.
So you assume that 100% of the dark matter is provided by this. 10 to minus 3, about 10 to minus a fraction of that goes into the black.
Yes.
Eventually.
Yes.
And the rest is in stars. So because or like in the ordinary variants, so you have just gas.
Normal star maybe, and gas.
No, gas.
Yeah, non-black hole.
In the universe today, most of the variants are gas.
Yeah.
Right, there's someone's question. Yeah.
What's the so you have dark photon? What's the CNV constraints on dark radiation in your mind?
Yeah.
That is an effective constraint.
Yeah.
And in my example, I use the ratio, the temperature ratio to be extremely small. Let's see how I use. Yeah, I use 2%. And then rho goes like the full power of 2% is extremely low.
First one is when you say pH is involved, at least it shouldn't be kind of generated from inflation.
Yes. Primary record generated from scalar perturbation so that they can generate induced gravitational waves.
So maybe for raytime information, this is still low.
Yes.
And the second one is for the fraction of this dark black hole. I think for standard model, I think the operation better. So
Operation better, yeah.
Black hole is growing because there is a huge amount of the operation, and now our black hole, supermassive black hole have a larger fraction of energy density. But do you expect such larger?
Yeah, but then this mass function that I use is the mass function coming from the population 3-star formation. And population 3-star also form as a small seed and a big creep. I think the accretion in that sense is already built into this user.
Anything else?
Fun stuff.
So if not, let's thank him again.